there is a place on this planet where the water is hot enough to melt lead, where pressure would crush a human body into something unrecognizable, where no light has reached in recorded memory, and where, against every prediction science has ever made, life is thriving, not merely surviving, thriving, clustered around cracks in the ocean floor, in total darkness, bathed in water saturated with chemicals that would kill any surface organism in seconds. Entire ecosystems exist that owe nothing to the sun. They do not need sunlight. They do not need oxygen in the way we understand it. They do not need moderate temperatures or gentle conditions. They have built a world powered by the chemistry of the Earth itself, by volcanic heat and dissolved minerals, by reactions between rock and water that have been running since long before the first ray of sunlight touched the sea. We call them hydrothermal vent communities, and their discovery, barely half a century ago, did not just add a new chapter to marine biology. It tore out the foundation and demanded that the entire book be rewritten. Before these vents were found, there was a single unquestioned rule in the life sciences. All life depends on the sun. Photosynthesis captures solar energy. Plants feed animals, animals feed other animals. The entire web of life, from the smallest bacterium to the largest whale, was understood to be ultimately powered by sunlight. This was not a hypothesis. It was treated as a law. It was taught in every biology classroom, published in every textbook, and assumed in every model of how life functions on Earth and how it might function elsewhere. That law is broken, not weakened, not modified, broken. The organisms found at hydrothermal vents derive their energy from chemical reactions that have nothing to do with sunlight. They feed on hydrogen sulfide, on methane, on hydrogen gas, on compounds that are toxic to surface life. They live in temperatures that exceed 300 degrees Celsius. They withstand pressures that would flatten a nuclear submarine. And they do all of this in a darkness so complete that the concept of day and night has no meaning. What does it mean when the most fundamental rule of biology turns out to be wrong? What does it mean when the definition of habitable, the very concept of where life can exist, has to be expanded by orders of magnitude? What does it mean when the strangest, most alien creatures on Earth are not found on some distant moon or orbiting a far-off star, but right here, beneath our own oceans, in places we had dismissed as barren? It means everything we thought we knew about life needs to be reconsidered. Every assumption about what life requires, where life can persist, and how life sustains itself is now open for revision. And the revision is not subtle, it is radical. Consider the scope of what has changed. For centuries, the search for life, whether on Earth or on other worlds, was guided by a single principle: follow the light. Life exists where the sun shines. It exists in the warm illuminated surface layer of the ocean. It exists on land where photosynthesis can fuel forests and grasslands. It exists in shallow lakes and rivers where algae and aquatic plants convert sunlight into food. Everywhere we looked, light meant life. Darkness meant death. This was considered so obvious, so self-evident, that it was barely questioned. Then we went to the bottom of the ocean, and we found entire civilizations built in total darkness. Not fragile, desperate colonies, clinging to existence at the edge of death. Dense, productive, species-rich ecosystems, humming with biological activity, powered by the chemistry of the planet's interior, and utterly indifferent to whether the sun was shining or not. The emotional weight of this discovery is difficult to convey. It is as though we had spent our entire lives mapping the forests of a continent, carefully cataloguing every tree, every bird, every insect, and then one day we looked underground and found a second continent beneath the first, equally vast, equally alive, but running on entirely different rules. The deep ocean is that second continent, and we have barely scratched its surface. By the end of tonight, you're going to understand why a handful of volcanic cracks on the ocean floor have forced scientists to rethink the entire framework of biology. You are going to understand how creatures that should not exist have built civilizations in conditions that should be lethal. And you are going to understand why the discovery of these vents may be the single most important biological finding since the identification of the cell. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. This is a story about fire and water, about chemistry and survival, about a world beneath the waves that operates on rules so different from our own that the creatures living there might as well be from another planet. And the most unsettling part is not what we have found, it is what we have not yet found. Because the deep ocean, the largest habitat on Earth, remains almost entirely unexplored. We have mapped more of the surface of Mars than we have mapped of our own ocean floor. We have sent more people into orbit around the Earth than we have sent to the deepest trenches. The darkness beneath the waves is not just uncharted, it is, in the truest sense of the word, unknown. And what little we have seen has already rewritten biology. Now let's begin. To understand what scientists found at hydrothermal vents and why it matters so profoundly, we first need to understand where these vents exist, not just their location on a map, but their location in the architecture of the ocean itself. Because the ocean is not a single uniform body of water. It is a layered world, stratified by light and temperature and pressure, and each layer is a different universe. The surface of the ocean, the part most people know, is called the epipelagic zone. It extends from the waterline to a depth of approximately 200 meters. This is the zone of sunlight, the zone where photosynthesis is possible, the zone where coral reefs bloom, where schools of fish shimmer in the light, where whales breach and dolphins leap, and the water is warm enough, bright enough, and oxygenated enough to support the vast majority of marine life that humans have ever observed. 200 meters. That is all the sunlight gets. In an ocean that averages 3,688 meters in depth, sunlight penetrates less than 6% of the water column. Everything below that thin, bright layer exists in varying degrees of darkness. To grasp what this means, consider a comparison. If the entire depth of the ocean were represented by a 10-story building, sunlight would penetrate only the first floor. The remaining 9 stories would exist in permanent darkness. Everything we know about marine life, the coral reefs, the schools of tuna, the sea turtles, the whales, the dolphins, all of it exists in that single illuminated floor. The rest of the building, the vast majority of the ocean's volume, is a world that most humans have never seen, and that most scientists, until very recently, assumed was essentially lifeless. That assumption was wrong. But before we get to why it was wrong, we need to understand what exists in those dark floors. Because each layer of the ocean is its own world, with its own physics, its own challenges, and its own solutions to the problem of survival. Pressure is the defining characteristic of the deep ocean, and it increases with a mathematical certainty that is both simple and terrifying. At the surface, the pressure is 1 atmosphere, the standard air pressure at sea level. For every 10 meters of additional depth, the pressure increases by approximately 1 additional atmosphere. At 100 meters, the pressure is 11 atmospheres. At 1,000 meters, it is 101 atmospheres. At the bottom of the Mariana Trench, nearly 11,000 meters down, the pressure exceeds 1,080 atmospheres. This is the equivalent of bearing a weight of more than 1 metric ton on every square centimeter of surface. Imagine a column of water 11 kilometers tall, pressing down on everything beneath it, compressing the water itself, squeezing every molecule, every cell, every organism into a state that surface biology considers impossible. Below the epipelagic zone lies the mesopelagic zone, the twilight zone, stretching from 200 to 1,000 meters. Here, sunlight still exists, but only as a faint blue-green whisper, too dim for any plant to use, too weak to warm the water. The creatures in this zone live in a permanent state of dusk. Many have evolved enormous eyes, proportionally larger than any land animals, to capture whatever traces of light remain. Others have abandoned vision entirely, relying instead on pressure-sensitive lateral lines, on chemical detection, on the ability to sense the faintest electrical fields generated by the muscles of nearby organisms. The twilight zone is also the domain of one of the ocean's most extraordinary daily events, the diel vertical migration. Every evening, as the sun sets and the surface darkens, billions of organisms rise from the mesopelagic zone toward the surface to feed on the plankton-rich waters above. Every morning, as the sun rises, they descend again, retreating into the relative safety of the deep. This migration involves more biomass than any other animal movement on Earth. It happens every single day. And it was not documented until the mid-20th century when sonar operators aboard naval vessels noticed a mysterious layer on their instruments that appeared to rise and fall with the cycle of day and night. They called it the deep scattering layer. They thought it was a false bottom, a phantom seafloor. It turned out to be life, in quantities that defied expectation. Below 1,000 meters, all sunlight vanishes. This is the bathypelagic zone, the midnight zone, and it extends from 1,000 to 4,000 meters beneath the surface. The temperature here hovers between 1 and 4 degrees Celsius, barely above freezing. The pressure is immense, hundreds of atmospheres bearing down on every surface, every body, every cell. And the darkness is absolute. Not dim, not fading, absolute. No photon of sunlight has ever penetrated to this depth. The only light that exists here is made by the organisms themselves, through a process called bioluminescence. Bioluminescence is the production of light by a living organism through a chemical reaction. It involves a light-emitting molecule called luciferin and an enzyme called luciferase that catalyzes its oxidation. The reaction produces visible light with almost no heat, an efficiency that surpasses any artificial light source ever designed. An incandescent bulb converts roughly 5% of its energy into light. A bioluminescent organism converts more than 90%. In the midnight zone, where energy is scarce and every calorie counts, this efficiency is not a luxury, it is a necessity. An estimated 76% of deep-sea organisms produce their own light. They use it to hunt, dangling glowing lures in front of gaping mouths. They use it to hide, coating their bellies in a dim glow that matches the faint light from above, a technique called counter-illumination that erases their silhouette from predators below. They use it to communicate, flashing coded patterns to attract mates across the void. And they use it to defend, ejecting clouds of luminous particles that blind and confuse attackers while the prey vanishes into the dark. Roll footage. Bioluminescent marine creatures pulsing with blue and green light in the midnight zone. Lanternfish with rows of photophores glowing along their bellies. Clouds of luminous organisms drifting through absolute blackness. The deep-sea anglerfish dangling its luminous lure. The deep-sea anglerfish is perhaps the most famous example of bioluminescent predation. This creature extends a modified dorsal spine that functions as a fishing rod, tipped with a bioluminescent lure produced by symbiotic bacteria. The anglerfish waits, motionless, in the absolute dark, its mouth open, its lure glowing. Smaller fish, drawn by the light, swim toward it. They do not see the predator, they see only the light. By the time they realize the danger, they are already inside the mouth. But the anglerfish is far from the only innovator in the midnight zone. The hatchetfish, a small silvery creature found between 200 and 1,000 meters deep, uses rows of photophores along its underside to project a faint glow that precisely matches the color and intensity of the dim light filtering down from above. To a predator looking upward, the hatchetfish's silhouette simply disappears, erased by its own light. The vampire squid, Vampiroteuthis infernalis, which dwells at depths between 600 and 1,200 meters cons, does not release ink like its shallow water relatives. Instead, it ejects a cloud of bioluminescent mucus, a glowing spray that disorients predators while the squid retreats into the safety of the dark. And then there is the deep-sea dragonfish, Stomia's boa, which has evolved something that borders on the unbelievable. Most bioluminescent organisms produce blue or green light because these short wavelengths travel farthest through water. The dragonfish produces red light from specialized organs beneath its eyes. Nearly all deep-sea organisms are blind to red wavelengths. They cannot detect it. The dragonfish can. This means the dragonfish carries an invisible searchlight, illuminating its prey without being seen. It hunts with a frequency of light that its victims cannot perceive. This is not a minor adaptation. It is the biological equivalent of a predator with night vision goggles in a world where no one else can see in the dark. The siphonophores, colonial organisms that can stretch to lengths exceeding 40 meters, use bioluminescence to coordinate their collective behavior, sending pulses of light along their chains of interconnected bodies, like signals traveling through a living wire. Each individual in the colony has a role. Some are specialized for feeding, some for reproduction, some for swimming, and they communicate through patterns of light that we are only beginning to decode. The sheer prevalence of bioluminescence in the deep ocean hints at how important light production is in a world without sunlight. In the upper ocean, organisms hide from light or use it passively. In the deep ocean, organisms manufacture light, weaponize it, trade it for survival advantages, and deploy it in combinations that suggest a biological sophistication far beyond what we would expect from creatures living in the most extreme environment on the planet. Bioluminescence is not a curiosity of the deep. It is the deep ocean's most universal language, and bioluminescence is not limited to animals. Deep-sea bacteria produce light as well, and they do so for reasons that are still debated. Some bacteria glow only when they reach a critical population density, a phenomenon called quorum sensing, switching on their light genes only when enough cells are present to create a visible signal. This coordinated behavior suggests that bacterial bioluminescence is a form of communication, or possibly a mechanism for attracting hosts. Many deep-sea animals, including the anglerfish, do not produce their own light, but instead harbor bioluminescent bacteria in specialized organs. The relationship between the animal and its bacteria is ancient and intimate, a partnership in light that has been refined over millions of years. Below 4,000 meters lies the abyssopelagic zone, or the abyss. Extending from 4,000 to 6,000 meters, this is a world of near-freezing water, crushing pressure exceeding 400 atmospheres, and a landscape dominated by vast, flat plains of fine sediment. This sediment is the accumulated residue of a constant, silent rain of dead organic matter drifting down from the productive surface waters above, a phenomenon known as marine snow. Marine snow is the lifeline of the abyss. Every day, billions of tiny particles, dead plankton, fecal pellets, shed mucus, fragments of decomposing organisms, begin their long descent from the sunlit surface toward the deep ocean floor. The journey is slow. A particle of marine snow may take weeks to sink from the surface to the abyssal plain, drifting through progressively colder and darker water, tossed by currents, grazed by zooplankton, colonized by bacteria that begin breaking it down even as it falls. Most of these particles are consumed or dissolved during their descent, eaten by organisms in the water column, recycled into dissolved nutrients long before they reach the bottom. But a small and precious fraction, completes the journey intact. This fraction is the primary food source for the organisms of the abyssal plain, the crumbs that fall from the photosynthetic world above. In productive surface waters where phytoplankton bloom in dense clouds of green and brown, the rain of marine snow is relatively heavy, and the organisms on the bottom below live in comparative abundance. But beneath nutrient-poor surface waters, in the centers of the great oceanic gyres, where the surface is a biological desert, the rain of marine snow slows to almost nothing. The organisms on the bottom in these regions exist in a state of perpetual near-starvation, their metabolisms reduced to the barest minimum necessary for survival, waiting months or years between meals. Some deep-sea organisms have adapted to this scarcity by developing the ability to absorb dissolved organic matter directly from the water, extracting nutrition from molecules too small and too dispersed for most organisms to utilize. The contrast between the abyss and the hydrothermal vent could not be sharper. The abyss is quiet, cold, nutrient-poor, and utterly dependent on the surface world for its meager food supply. The hydrothermal vent is loud with chemical energy, hot with volcanic heat, rich with dissolved minerals, and completely independent of the surface. One is a desert, the other is an oasis, and both exist in the same vast, dark, pressurized world. And then there is the Hadal Zone, below 6,000 meters, named after Hades, the Greek god of the underworld. This is the domain of the ocean trenches, the deepest scars on the planet's surface, carved by the collision and subduction of tectonic plates. The Mariana Trench in the Western Pacific, the Tonga Trench in the South Pacific, the Kermadec Trench, the Philippine Trench, the Kuril-Kamchatka Trench. These are not simply deep places. They are geological wounds, places where one plate of the Earth's crust is being forced beneath another, diving into the mantle at rates measured in centimeters per year. The deepest of these, the Challenger Deep in the Mariana Trench, reaches a maximum known depth of approximately 10,935 meters, nearly 11 kilometers below the surface. If Mount Everest, the tallest mountain on land at 8,849 meters, were placed at the bottom of the Challenger Deep, its peak would still be submerged under more than 2,000 meters of ocean, 2 kilometers of water above the tallest point on Earth. The scale is almost impossible to hold in the mind. To put it another way, if a stone were dropped from the surface directly above the Challenger Deep, it would take more than an hour to reach the bottom, sinking through water that grew colder and denser with every passing second. A human voice, if it could somehow be projected downward, would take approximately 7 seconds for the sound to travel from the surface to the deepest point. 7 seconds of falling through darkness, through cold, through pressure that increases with every meter. By the time the sound arrives at the bottom, the world it describes, the surface world of air and light and warmth, is as remote as another planet. At that depth, the pressure exceeds 1,080 atmospheres, the equivalent of placing roughly 50 jumbo jet aircraft on a surface the size of a single human palm. Water at that pressure becomes denser, more compressed. Objects that are perfectly rigid on the surface will buckle, crack, and implode. A styrofoam cup taken to a depth of 3,000 meters returns the size of a thimble, its gas bubbles crushed to a fraction of their original volume by the relentless force of the water above. Researchers on deep-sea expeditions often send decorated styrofoam cups down, attached to the exterior of the submersible. The cups come back as tiny, dense souvenirs, perfect miniatures of the original, every detail preserved but every dimension reduced. It is a playful demonstration of a force that is, in practice, lethal. In 1960, Jacques Piccard and Don Walsh descended to the bottom of the Challenger Deep aboard the bathyscaphe Trieste. The descent took nearly 5 hours. 5 hours of sinking through water that grew colder, darker, and heavier with every passing minute. The Trieste was not a submarine in any conventional sense. It was a bathyscaphe, a deep-diving vessel consisting of a heavy steel cruise sphere with walls more than 12 centimeters thick, forged from a single piece of metal to eliminate structural weak points, suspended beneath a float filled with gasoline that provided buoyancy. Even this massive engineering was barely sufficient. The pressure at the bottom compressed the sphere by several millimeters. The viewing port cracked during the descent. Not shattered, but cracked. A sound that froze the blood of both men inside. They continued anyway. Roll footage. Dark, deep waters. A submersible descending through fading blue light into total blackness. External lights illuminating particles of marine snow drifting past like snow in reverse. Instrument readings climbing steadily. The hull groaning faintly under increasing pressure. They reached a depth of approximately 10,916 meters. They saw a flat, featureless expanse of pale sediment, stirred into a cloud by their arrival. And through the settling silt, Piccard reported seeing a flatfish, roughly 30 centimeters long, resting on the bottom. A living creature at the deepest point on Earth. That observation, debated for decades by scientists who questioned whether it was truly a flatfish or perhaps a sea cucumber, carried an implication that echoed through biology. Complex, multicellular life existed even at the most extreme depth. The ocean floor was not a dead zone, not even at 11 kilometers down. No human would return to that depth for more than 50 years. In 2012, filmmaker James Cameron descended solo to the Challenger Deep in the Deep Sea Challenger, a custom-built submersible designed specifically for the dive. The vessel was a radical departure from conventional submersible design. A vertical torpedo shape that descended feet first, with Cameron seated in a small steel sphere at the base. He spent approximately 3 hours at the bottom, the longest stay at the deepest point of any crewed visit. He collected sediment samples, filmed the seafloor with high-definition cameras, and reported seeing microbial mats but no fish or large organisms. In 2019, Victor Vescovo, an American explorer and retired naval officer, made the deepest dive in recorded history aboard the submersible limiting factor, a titanium-hulled vessel designed to be reusable at full ocean depth. Vescovo reached a depth of 10,928 meters, surpassing the Trieste's record by approximately 12 meters. More importantly, the limiting factor was designed for repeated dives, not a single record attempt. Vescovo went on to complete dives to the deepest points of all 5 of the world's oceans, the Atlantic, Pacific, Indian, Arctic, and Southern, becoming the first person in history to accomplish this feat. At the bottom of every ocean, in every trench, he and his team found signs of life. They also found something else, something far less inspiring. At the bottom of the Mariana Trench, Vescovo's team observed a plastic baguette and candy wrappers resting on the sediment. Human pollution had reached the deepest point on the planet. The same trenches that harbour life forms, found nowhere else on Earth, also contain the refuse of surface civilization, carried there by ocean currents and gravity. The reach of human impact extends to the very bottom of the world. But even these modern expeditions covered only tiny patches of the Hadal Zone. The Mariana Trench alone stretches for approximately 2,550 kilometers. The total area of all Hadal trenches on Earth exceeds 2 million square kilometers. The number of human visits to these depths can be counted on 2 hands. Fewer people have been to the bottom of the ocean than have walked on the surface of the moon. This is the architecture of the deep ocean, a vertical world layered by light and pressure, ranging from the warm, sunlit surface to a darkness so total and a pressure so immense that it defies human experience. And it is within this architecture, along the volcanic ridges and tectonic boundaries, where the Earth's crust is pulling apart or crashing together, that the most extraordinary discovery in the history of biology was made. The mid-ocean ridge system, the network of volcanic ridges where tectonic plates spread apart, is the largest geological feature on the planet. It stretches for approximately 65,000 kilometers, winding through every major ocean basin like a seam running around the Earth. Along this ridge, new ocean floor is constantly being formed as magma rises from the mantle, cools, and solidifies. And along this ridge, hydrothermal vents are scattered like chimneys on a vast, dark factory floor, each one a point of intense chemical activity, each one a potential cradle for life that owes nothing to the sun. The ridge is not a single, unbroken line. It is segmented, offset by transform faults, and varies dramatically in character from one region to another. In some places, like the East Pacific Rise, the ridge is spreading rapidly, at rates exceeding 15 centimeters per year, producing a broad, relatively smooth ridge with abundant volcanic activity and frequent hydrothermal venting. In other places, like the Mid-Atlantic Ridge, the spreading rate is much slower, typically less than 3 centimeters per year, producing a deeper, more rugged ridge with a prominent central rift valley. The characteristics of the hydrothermal vents in each region reflect these geological differences. Fast-spreading ridges tend to host more numerous but shorter-lived vents. Slow-spreading ridges tend to produce fewer vent sites, but some of those sites may persist for thousands or even hundreds of thousands of years. The ridge system is also the site of continuous seismic activity. Thousands of small earthquakes occur along the mid-ocean ridge every year, most too faint to be detected on land, but registered by the global network of underwater seismometers. These earthquakes result from the constant stretching and fracturing of the crust as the plates move apart. Each earthquake opens new pathways for seawater to penetrate into the hot rock below. Each creates new channels for superheated water to rise back toward the surface. Each potentially gives birth to new hydrothermal vents. The ridge is not static. It is a dynamic, restless, continuously evolving system, driven by the same forces that move continents and raise mountains. Scientists now estimate that there are hundreds of known active hydrothermal vent fields on the ocean floor, with thousands of individual vent structures. Many have never been observed. The deep ocean is so vast, and the technology to explore it so limited, that the majority of these vent systems remain entirely unknown. What this means is staggering. There are entire ecosystems on our planet, living communities powered by chemical energy from the Earth's interior, that no human being has ever seen. They exist right now, at this moment, and we do not know they are there. That is the foundation. That is the scale. And that is the starting point for everything that follows. The story begins not with a discovery, but with a prediction. In the early 1970s, geophysicists studying the mid-ocean ridge system predicted that hot water should be venting from the seafloor at certain locations. The theory was straightforward. Seawater seeps down through cracks in the oceanic crust, penetrates deep into the rock where it encounters magma or superheated rock near the mantle, absorbs heat and dissolves minerals, and then rises back to the seafloor as a plume of hot, chemically altered fluid. The process is called hydrothermal circulation, and the physics demanded that it was happening. The only question was where and whether anyone would ever see it. J-roll footage. Scientists aboard a research vessel preparing instruments for a deep-sea dive, crew members studying sonar charts of the mid-ocean ridge, a submersible being lowered into dark water from the stern of the ship, researchers in orange survival suits watching from the deck. In 1977, a team of scientists aboard the research vessel Knorr, using the deep submergence vehicle Alvin, descended to the Galapagos Rift in the eastern Pacific Ocean. The team included geochemist John Edmund and geologist Jack Corliss, among others. Alvin was, and remains, one of the most important tools in the history of ocean science. First launched in 1964, it is a 3-person submersible capable of reaching depths of approximately 4,500 meters. It has completed more than 5,000 dives. It helped locate the wreck of the Titanic in 1985. But its most important contribution to human knowledge was this dive, this descent to a crack in the seafloor near the Galapagos Islands. The scientists expected to find warm springs, perhaps some unusual mineral deposits. They had deployed temperature sensors and towed camera systems in advance, and the data suggested that hot fluid was escaping from the seabed. They thought they knew what they would find. They were wrong. As Alvin descended to approximately 2,500 meters, the temperature readings began to spike. Then the submersible's lights illuminated something no human being had ever witnessed. Shimmering water, wavering like heat haze over a desert road, rising from cracks in dark volcanic rock. Columns of mineral-rich fluid, some of them black with dissolved metals, billowing upward like smoke from an underwater chimney. And clustered around these chimneys, in densities that seemed physically impossible at that depth, life. Not the sparse, ghostly life of the abyssal plain. Not the occasional sea cucumber or translucent shrimp drifting through the dark. Dense, thriving, extravagant life. Organisms packed together so tightly that they covered the seafloor in living carpets. Creatures of a kind that no biologist had ever imagined. The most conspicuous were the giant tube worms, later classified as Riftia pachyptilla. These worms grew in clusters around the vents, their bodies encased in white, chitinous tubes that could reach lengths of more than 1.5 meters. From the top of each tube extended a brilliant crimson plume, a feathery structure rich in blood vessels, waving gently in the warm currents. The red color came from hemoglobin, the same oxygen-carrying molecule found in human blood. But in the tube worms, the hemoglobin served a different and dual purpose. It carried not only oxygen, but also hydrogen sulfide, the toxic gas that poured from the vents, and transported both to a specialized organ inside the worm's body called the trophosome. Roll footage. Hydrothermal vent chimneys releasing billowing plumes of dark, mineral-laden water, giant tube worms with crimson plumes clustered densely around ventile openings, shimmering superheated water, rising from cracks in basalt, pale crabs, and shrimp moving across mineral-encrusted rock surfaces. The trophosome is one of the most remarkable organs in the animal kingdom. It is a spongy lobed tissue that fills most of the worm's body cavity, and it is packed with billions of chemosynthetic bacteria. These bacteria take the hydrogen sulfide delivered by the worm's hemoglobin and use it as an energy source, oxidizing the sulfide and using the released energy to fix carbon dioxide into organic molecules. The worm provides the bacteria with a steady supply of raw materials. The bacteria provide the worm with food. Neither can survive without the other. This partnership is so complete that the adult tube worm has no mouth, no stomach, no intestines, no digestive system of any kind. It does not eat in any conventional sense. It does not need to. The bacteria inside its trophosome do all the feeding, converting volcanic chemicals into the molecules that the worm's body requires. The tube worm is, in a very real sense, an animal that runs on volcanic energy, an animal that eats rock chemistry. The growth rate of Riftia pachyptila is another source of astonishment. These worms can grow at rates exceeding 85 centimeters per year, making them among the fastest-growing marine invertebrates known. In the nutrient-poor deep ocean, where most organisms grow at agonizingly slow rates, the tube worms are almost explosive in their development. This rapid growth is powered by the enormous productivity of their chemosynthetic bacteria, which can fix carbon at rates comparable to the most productive photosynthetic systems on the surface. A single tube worm colony, clustered around an active vent, can produce biomass at rates that would be exceptional, even in a tropical rainforest. The oasis metaphor is not an exaggeration. In terms of biological productivity per unit area, a healthy hydrothermal vent community rivals the most fertile ecosystems on the planet. But rapid growth comes at a cost. The tube worms are utterly dependent on the continued flow of vent fluid. If the geological conditions shift and the vent dies, the tube worms die with it, often within weeks. They have no ability to move, no ability to seek a new vent, no ability to survive without the constant supply of hydrogen sulfide and warmth. Their lives are tied to the geological clock, to the unpredictable rhythms of volcanism and tectonics that open and close vents across the mid-ocean ridge. They live fast, grow fast, and die fast, at least in geological terms. But here's the problem. The tube worms were only the beginning. As subsequent expeditions explored more vent sites across the Pacific, the Atlantic, and eventually the Indian and Arctic Oceans, the catalogue of organisms grew rapidly and bewilderingly. There were dense beds of giant clams, Calyptogena magnifica, some exceeding 30 centimeters in length, their tissues harboring their own populations of chemosynthetic bacteria that metabolized hydrogen sulfide in exchange for a protected environment. There were mussels, Bathymodilus thermophilus, packed in clusters so dense that they resembled the mussel beds of rocky shorelines, but fed not by filtering surface plankton, but by symbiotic bacteria powered by methane and hydrogen sulfide. There were ghostly white crabs, Bythagria thermidron, blind and unpigmented, their bodies as pale as bone, because in a world without light, colour serves no purpose. There were swarms of vent shrimp, Rimicaris exoculata, discovered at vent sites along the mid-Atlantic ridge, whose eyes had evolved into a form unlike any other known animal. These shrimp do not have conventional eyes with lenses and retinas. Instead, they possess a broad, flat, photoreceptive organ on their backs that is sensitive to the faint infrared glow emitted by the superheated vent fluid. They do not see in the way surface animals see. They sense the thermal radiation of the vents themselves, using the heat signature of the water to navigate toward or away from the scalding fluid. They are, in effect, seeing heat, and they do this in a world where no other form of vision is possible. The lives of these shrimp are a constant negotiation between nourishment and death. They need to be close to the vent fluid because their food source, the chemosynthetic bacteria that grow on their modified mouthparts and gill chambers, requires the sulfide-rich water that flows from the chimney. But they must not get too close, because the superheated water will cook them alive. The shrimp crowd around the vents in dense swarms, their bodies packed together, their heat-sensing organs constantly monitoring the thermal gradient, adjusting their position by fractions of a centimeter to stay in the narrow zone where the chemistry is right and the temperature is survivable. A misstep of a few centimeters in the wrong direction means death. The Pompeii worm, Alvinella pompeiana, named after both the submersible Alvin and the Roman city destroyed by volcanic eruption, lives closer to the vent openings than perhaps any other multicellular organism on Earth. Its tail end is anchored inside a tube attached directly to the chimney wall, where temperatures can exceed 80 degrees Celsius. Its head end extends into the cooler surrounding water, where temperatures may be only 20 degrees Celsius. The worm lives in a thermal gradient of 60 degrees or more across the length of its own body, a temperature difference that would be lethal to virtually any surface organism. On its back, it carries a dense mat of filamentous bacteria that form a kind of living blanket. These bacteria may provide thermal insulation, helping to protect the worm from the extreme heat, and in return, the worm provides the bacteria with a stable surface and access to the chemical-rich vent fluid. It is a partnership forged in fire. Each of these organisms represented a violation of established biological principles. The tube worms violated the assumption that all animals need a digestive system. The chemosynthetic bacteria violated the assumption that all primary production requires sunlight. The vent shrimp violated the assumption that functional vision requires visible light. The Pompeii worm violated the assumption that multicellular animals cannot survive at temperatures exceeding 50 degrees Celsius. And all of them, collectively, violated the most fundamental assumption of all, that life on Earth is a solar phenomenon. The science behind these violations centers on a single process: chemosynthesis. This is the production of organic molecules using energy derived from chemical reactions rather than from sunlight. In photosynthesis, the energy source is light. In chemosynthesis, the energy source is chemistry, specifically the oxidation of reduced compounds like hydrogen sulfide, methane, or hydrogen gas. The chemistry is elegant in its simplicity. Hydrogen sulfide, which pours from hydrothermal vents in enormous quantities, is a reduced compound, meaning it contains electrons in a high-energy state. When chemosynthetic bacteria oxidize hydrogen sulfide, they strip away those high-energy electrons and use them to drive the fixation of carbon dioxide into organic carbon. The process is analogous to photosynthesis, but with a different energy input. Instead of photons from the sun, the bacteria use electrons from volcanic chemicals. The result is the same: organic molecules, food, the base of a food web that operates in complete independence from sunlight. And it gets stranger, because chemosynthesis turned out to be not just an alternative to photosynthesis. In some environments, it may be more ancient, more widespread, and more fundamental to the history of life on this planet than photosynthesis itself. The vent ecosystems were only the first example. In the years following the Galapagos discovery, scientists found chemosynthetic communities in other settings as well. Cold seeps, locations where methane and hydrogen sulfide ooze slowly from the seafloor without any volcanic heat, were discovered along continental margins, in the Gulf of Mexico, off the coast of Oregon, and in many other locations. These cold seep communities looked superficially similar to vent communities, with dense beds of mussels and clams, mats of bacteria, and clusters of tube worms. But they were powered by different chemistry and existed at different temperatures. The cold seep tube worms, belonging to the genus Lamellibrachia, grew far more slowly than their vent cousins, but lived far longer, with individual worms estimated to survive for more than 250 years. They were among the longest-lived animals on Earth. The discovery of cold seeps meant that chemosynthetic life was not confined to the narrow zones of volcanic activity along the mid-ocean ridge. It could exist anywhere that reduced chemicals seeped from the seafloor, which turned out to be an enormous number of locations. Cold seeps are found along virtually every continental margin in the world. Wherever organic matter buried in sediment is broken down by microbial activity, releasing methane and sulfide that percolate upward to the surface. The total area of seafloor that supports chemosynthetic communities, when vents, cold seeps, and other reducing environments are considered together, is far larger than anyone had imagined. Consider the metabolic diversity found at vent sites alone. Some bacteria oxidize hydrogen sulfide, others oxidize methane, others oxidize iron or manganese or ammonia or hydrogen gas. Each of these reactions releases energy that can be harnessed for carbon fixation. Each represents a different way of powering life without the sun. The diversity of chemosynthetic pathways is not a marginal phenomenon. It is vast. It suggests that the ability to derive energy from chemical reactions is deeply embedded in the fundamental fabric of living systems, that it may have preceded photosynthesis, and that it may represent the original mode of biological energy acquisition. The implications are difficult to overstate. If chemosynthesis came first, then the story of life on Earth is not the story of sunlight and photosynthesis. It is the story of chemistry and rock. The sun is not the original engine of life. It is a latecomer, a powerful but relatively recent addition to a biosphere that was already running on volcanic energy and rock chemistry. long before the first photosynthetic organism captured its first photon. This idea, sometimes called the chemo-autotrophic origin hypothesis, has gained significant support in recent decades. Molecular phylogenetics studies, analyses of the evolutionary relationships among organisms based on their DNA and protein sequences, have placed chemosynthetic lineages near the root of the tree of life, suggesting that the earliest organisms were chemical feeders rather than light feeders. Geological evidence indicates that the conditions necessary for chemosynthesis, hot water circulating through volcanic rock, were present on the early Earth long before the atmosphere became transparent enough for significant amounts of sunlight to reach the surface. And thermodynamic calculations show that the energy available from reactions between water and rock is sufficient to sustain life, even in the absence of any other energy source. None of this proves that chemosynthesis came first. It is an active area of research with competing hypotheses and unresolved debates. But the evidence from hydrothermal vents has fundamentally shifted the balance of the argument. The deep ocean is no longer a footnote in the story of life on Earth. It may be the opening chapter. In 2000, a discovery was made that pushed the boundaries even further. Marine geologist Donna Blackman and a research team found a vent field unlike any previously known, located on the mid-Atlantic ridge at a depth of approximately 700 to 800 meters. The site was named the Lost City, and it was unlike the black smokers of the Galapagos Rift in almost every way. The Lost City vents are not powered by magma. They are powered by a chemical process called serpentinization, in which seawater reacts with a type of rock called peridotite, a rock from the Earth's upper mantle that is exposed at the seafloor in certain geological settings. When peridotite reacts with water, it produces heat, hydrogen gas, and methane, all without the involvement of volcanic magma. The temperature of the Lost City vent fluids is moderate, between 40 and 90 degrees Celsius, far cooler than the 350-degree water of black smokers. The chimneys are not built from dark metal sulfides. They are built from calcium carbonate, the same mineral found in limestone and seashells. Some of these carbonate chimneys tower 60 meters above the seafloor, pale white pillars rising from the darkness like the columns of an ancient temple. Oceanographer Deborah Kelly of the University of Washington has led long-term study of the Lost City, deploying instruments and cameras that have monitored the vent field for years. Her work has revealed that the Lost City is remarkably stable, with some chimneys estimated to have been active for more than 100,000 years. This is a stark contrast to the black smokers, which are ephemeral features that typically last only decades to centuries. The Lost City is not a flash of volcanic activity. It is a slow, steady chemical engine that has been running for geological ages. The significance of the Lost City is profound. It proves that hydrothermal activity does not require volcanic magma. It only requires the interaction of water and rock. Serpentinization can occur wherever mantle rock is exposed to water, and this is a far more common geological scenario than active volcanism. It means that chemosynthetic life could potentially be sustained in a much wider range of environments than previously imagined, not just at volcanic ridges, but anywhere that the right kind of rock meets water. The biological communities at the Lost City are distinct from those at black smokers. Instead of the giant tube worms and large clams found at hot vents, the Lost City hosts dense populations of tiny snails, amphipods, and a specialized community of archaea, single-celled organisms that are distinct from both bacteria and more complex life. These archaea are methanogens, organisms that produce methane as a byproduct of their metabolism, and they thrive in the alkaline, hydrogen-rich fluids of the Lost City. They represent some of the most ancient metabolic strategies known to biology, strategies that may have been among the first to emerge in the history of life. The Lost City also raises questions about the conditions under which life might first have arisen. Some researchers have argued that the alkaline, hydrogen-rich environment of serpentinization-driven vents provides a better model for the origin of life than the acidic, superheated environment of black smokers. The moderate temperatures, the abundance of hydrogen and methane, the formation of thin mineral membranes, that could have served as natural compartments for early chemical reactions. All of these features make the Lost City a compelling candidate for the type of environment where the chemistry of life might first have become organized into self-sustaining systems. And this is where the answer becomes deeply unsettling, because the conditions at the Lost City, moderate temperatures, alkaline fluids, hydrogen and methane as energy sources, are precisely the conditions that many astrobiologists believe could exist on other worlds. On Europa, the ice-covered moon of Jupiter, which harbours a global ocean beneath its frozen surface. On Enceladus, the small moon of Saturn that is actively venting water vapour, hydrogen gas and organic molecules into space. On any icy world with a subsurface ocean and a rocky interior where serpentinization could occur. The Lost City is not just a geological curiosity on Earth. It may be a template for life throughout the cosmos. The expedition history of hydrothermal vent research reads like a chronicle of escalating astonishment. In 1979, 2 years after the Galapagos discovery, black smokers were first observed at a site called 21 North on the East Pacific Rise. These vents were releasing water at temperatures exceeding 350 degrees Celsius, and the chimneys were built from massive deposits of metal sulfides rich in copper, zinc, and gold. The mineral wealth concentrated at these sites immediately attracted the attention of the mining industry, a complication that continues to this day. In 1985, vent communities were discovered on the Mid-Atlantic Ridge, proving that chemosynthetic ecosystems were not confined to the Pacific. In the 1990s, vents were found in the Indian Ocean, in the Arctic, in the waters surrounding Antarctica. Each new discovery expanded the map. Each new site revealed organisms uniquely adapted to local conditions. The vent communities of the Atlantic were dominated by different species than those of the Pacific. The Arctic vents harbored creatures found nowhere else. The pattern was consistent. The more scientists looked, the more they found. And the more they found, the more they realized how little they knew. J-roll footage. Scientists in a research vessel control room watching a live video feed from a remotely operated vehicle exploring a vent site. Researchers carefully handling sample containers in a shipboard laboratory. A team deploying a sensor package over the stern of a vessel at night. The glow of screens reflected on focused faces. But here's what makes this truly terrifying. After nearly 5 decades of exploration, after hundreds of submersible dives and remotely operated vehicle surveys, after the deployment of seafloor observatories and the analysis of thousands of samples, the overwhelming consensus among deep-sea scientists is that we have explored less than 5% of the global mid-ocean ridge system with any meaningful resolution. Less than 5%. The ridge stretches for 65,000 kilometers. We have surveyed a small fraction of it. The vast majority of hydrothermal vents on this planet have never been seen by human eyes or instruments. The organisms living at those vents have never been described, catalogued, or studied. They exist right now in the darkness, and we know nothing about them. To put this in perspective, consider what we have found in that small fraction. More than 700 species of organisms have been described from hydrothermal vent environments. Many of these species are found nowhere else on Earth. Some entire families of organisms have been discovered at vents, groups so different from anything previously known that they required the creation of new taxonomic categories. And all of this from less than 5% of the available habitat. What might be living at the other 95%? The honest answer is that we have no idea. The patterns we have observed suggest that different vent sites in different ocean basins host different communities of organisms shaped by local geological conditions, water chemistry, and the history of colonization. Vent communities in the Pacific are different from those in the Atlantic. Atlantic communities are different from those in the Indian Ocean. Arctic vents host species found nowhere else. If this pattern holds, and there is every reason to believe it does, then the unsurveyed vent sites of the world's oceans may contain hundreds or even thousands of species that have never been seen by any human being. The rate of discovery has not slowed. In every decade since the initial finding in 1977, new vent fields have been located, new species have been described, and new biological processes have been documented. In the 2000s, Vents were found at unexpected locations, including along the Arctic mid-ocean ridge and in the Southern Ocean near Antarctica. These high-latitude vents hosted communities adapted to water temperatures even colder than those found at lower latitudes, with species compositions that were entirely unique. Each new discovery reinforced the same lesson. The deep ocean is more diverse, more active, and more full of life than any model has predicted. Then something happened that changed the urgency of this work. The mining industry arrived. The discovery of hydrothermal vent ecosystems opened a door that has never been closed. Behind that door lay a series of mysteries, each more unsettling than the last, each revealing a deeper and more uncomfortable truth about how little we understand the biology of our own planet. The vents were only the beginning. What scientists found when they looked beyond the vents into the broader landscape of the deep ocean was a world that refused to conform to the rules of surface biology in any predictable way. Consider the brine pools. These are among the most alien environments on Earth, places where the language of terrestrial biology barely applies. Found primarily at the bottom of the Gulf of Mexico, the Red Sea, and parts of the Mediterranean, brine pools are collections of water so saturated with dissolved salt that they form a distinct body of liquid on the ocean floor, a lake beneath the sea. The brine is 3 to 8 times saltier than normal seawater. It is often laced with dissolved methane, hydrogen sulfide, and other toxic compounds, and it is so dense that it forms a visible surface, a shore, a waterline, on the deep ocean floor, as sharply defined as the edge of a freshwater lake on land. The interface between the brine pool and the surrounding seawater, a thin region called the halocline, is a zone of extreme chemical gradients. Over a distance of just a few centimeters, the salinity can change by a factor of 5. The dissolved oxygen drops to near zero. The concentration of toxic gases spikes. For most organisms, crossing this boundary is lethal. The brine pool is, to the vast majority of marine life, a lake of death. Organisms that stumble into it are preserved, pickled by the extreme salinity, their bodies lying on the brine shore like driftwood on a beach. And yet, life exists there. Dense mats of bacteria thrive at the halocline, feeding on the methane and sulfide that diffuse upward from the brine. Mussels, adapted to tolerate the extreme chemistry, cluster along the edges. Specialized polychaete worms burrow into the sediment near the brine margin, and within the brine itself, in water so hostile that it dissolves the shells of organisms that fall in. Microbial communities persist, running metabolisms that operate at the very edge of what biology can sustain. They are alive, but only barely, and by rules that we are only beginning to understand. In the Red Sea, one of the most extreme brine pools known sits at a depth of approximately 2,000 meters, called the Atlantis II Deep. It was first discovered in the 1960s and has been studied intermittently ever since. The brine here reaches temperatures exceeding 68 degrees Celsius and has a salinity more than 7 times that of normal seawater. It is saturated with dissolved metals, including zinc, copper, silver, and gold. The pool is essentially a toxic, superheated, hypersaline bath of dissolved mineral treasure. And in this bath, microorganisms survive, not merely persist in a dormant state, but actively metabolize, cycling carbon and sulfur and nitrogen in ways that challenge our understanding of biochemical limits. The Atlantis Deep alone contains an estimated 94 million tons of mineral-rich sediment. The economic value of these deposits has been estimated at billions of dollars. This, predictably, has attracted commercial interest. Saudi Arabia and Sudan, the nations whose coastlines border the relevant section of the Red Sea, have been in discussions about the potential for mining these deposits for decades. The International Seabed Authority, a United Nations body, has already granted exploration licenses covering more than 1 million square kilometers of the deep ocean floor in various locations worldwide. The race to extract mineral wealth from the deep sea has begun, and it is accelerating. The numbers are striking. A single brine pool in the Red Sea contains more metallic ore than many of the world's largest terrestrial mines. The total mineral wealth locked in deep-sea brine pools, hydrothermal vent deposits, and polymetallic nodule fields worldwide has been estimated in the trillions of dollars. But the organisms living in these environments are not replaceable. They are not interchangeable with surface life. They represent unique biological solutions to extreme conditions, solutions that may hold the key to understanding life beyond Earth. Mining them into oblivion before we understand them would be an act of profound and irreversible ignorance. But the brine pools, strange as they are, represent only one facet of the mystery. Consider deep-sea gigantism. This is the observed tendency of certain deep-sea organisms to grow far larger than their shallow water or terrestrial relatives. Giant isopods, crustaceans related to the common woodlouse, grow to lengths exceeding 40 centimeters in the deep sea, roughly 14 times the size of their land-dwelling cousins. Giant amphipods have been recovered from Hadal trenches, their translucent bodies reaching sizes that should not be possible for organisms with their metabolic constraints. The Japanese spider crab, living at depths up to several hundred meters, can have a leg span exceeding 3.5 meters. The colossal squid, Mesonachoteuthis hamiltoni, which inhabits the deep waters of the Southern Ocean, achieves total lengths exceeding 12 meters and possesses the largest eyes in the animal kingdom, each one approximately 27 centimeters in diameter, roughly the size of a dinner plate. Those eyes are not decorative. They are precision instruments, evolved to detect the faintest bioluminescent flashes in the absolute darkness, capable of sensing light at levels that human instruments struggle to measure. Each eye contains a built-in headlight, a photophore that can illuminate whatever the squid is looking at, like a diver with a built-in flashlight. Why do deep-sea organisms grow so large? Several hypotheses have been proposed. The cold temperatures of the deep ocean may slow metabolic rates, allowing organisms to grow for longer periods before reaching reproductive maturity. The elevated pressure may alter cell chemistry in ways that favor larger body sizes. The scarcity of food in the deep may select for larger individuals who can store more energy and survive longer between meals. Reduced predation pressure may remove the selective advantage of being small and agile, allowing organisms to invest energy in growth rather than speed. Some researchers have proposed that elevated dissolved oxygen levels at certain depths promote larger body sizes by allowing more efficient respiration. Each of these hypotheses has evidence in its favor. None of them fully explains the phenomenon. Deep-sea gigantism remains an open question, a puzzle that reminds us that the deep ocean operates by rules we have not fully cracked. What makes the gigantism question particularly frustrating is that it highlights a broader problem in deep-sea biology. We can observe the phenomenon, we can measure it, we can photograph giant isopods and colossal squid and record their dimensions with precision, but we cannot explain why it happens, because we do not understand the fundamental metabolic and environmental conditions well enough to build a satisfying model. The deep ocean presents us with facts that outrun our theories. We see the results of processes we cannot yet describe, outcomes of forces we cannot yet quantify. This gap between observation and understanding runs through every aspect of deep-sea science. We can describe what hydrothermal vent organisms look like, where they live, what they eat, and how they reproduce. But we cannot fully explain how they arrived at their current locations, how they maintain genetic diversity across isolated populations, or how they will respond to environmental changes that we ourselves are causing. Our knowledge is broad but shallow, a description of surfaces without a penetration to the mechanisms beneath. Then there is the matter of unexplained ocean sounds. In 1997, the National Oceanic and Atmospheric Administration of the United States detected an ultra-low frequency sound in the Pacific Ocean using a network of underwater microphones called hydrophones. These hydrophones had originally been deployed during the Cold War to detect submarine activity. After the Cold War ended, the network was repurposed for scientific research, listening to the sounds of the ocean itself. And the ocean, it turned out, was full of sounds that no one had expected. The sound detected in 1997 was one of the loudest underwater sounds ever recorded. It lasted approximately 1 minute. It was detected by sensors more than 5,000 kilometers apart, and its acoustic profile, its frequency structure and amplitude pattern, was consistent with a biological source, an animal call. But no known animal could produce a sound of that magnitude. The blue whale, the largest animal on Earth, produces calls that reach approximately 188 decibels. This sound was louder, significantly louder. The sound was named the bloop. It became famous, spawning endless speculation. Was it a creature larger than any whale? A deep-sea organism of unimaginable size, lurking in the abyss, producing calls that dwarfed those of the largest known animals? The possibility captured the public imagination and refused to let go. In 2005, NOAA revised its assessment. The most likely explanation, they concluded, was an icequake, the sound of a large iceberg fracturing or grinding against the ocean floor near Antarctica. The acoustic profile, when analyzed with more refined techniques, was consistent with cryogenic sources rather than biological ones. The mystery, for most scientists, was resolved, but the bloop was not the only unexplained sound in the ocean's acoustic record. The hydrophone network has recorded numerous other anomalous signals over the decades. The upsweep, a continuous sound detected since 1991, appears to originate from a volcanically active region in the South Pacific, and remains without a definitive explanation. The Julia, recorded in 1999, lasted approximately 15 seconds and sounded, to human ears, like a person calling out a name. It may have been an iceberg running aground. The slowdown, detected in 1997, was a gradually decreasing frequency sound that lasted approximately 7 minutes and was recorded across the entire Pacific basin. Its source has never been conclusively identified. The ocean's acoustic environment is far richer and more complex than most people realize. Sound travels through water at approximately 1,500 meters per second, roughly 4.5 times faster than in air. And because water is far denser than air, sound waves can travel enormous distances underwater with relatively little loss of energy. A whale's call can cross entire ocean basins. The crack of a volcanic eruption on the mid-ocean ridge can be heard by hydrophones thousands of kilometers away. The deep ocean is not silent. It is a vast echo chamber, filled with sounds from geological, biological, and atmospheric sources, most of which we cannot identify with certainty. In the late 1940s and early 1950s, the United States Navy deployed the SOFAR, or Sound Fixing and Ranging, Channel Network, a system of underwater microphones positioned at the depth where sound travels most efficiently. A layer in the water column where temperature and pressure condition cause sound waves to be refracted and trapped, creating a natural acoustic waveguide. Sounds produced at this depth can travel for thousands of kilometers with minimal loss of intensity. The Navy used the system to track submarine movements during the Cold War. After the system was partially declassified and made available to scientists, researchers discovered that the ocean was full of sounds that had never been recorded before. Some were readily identifiable as whale calls, earthquakes, or volcanic eruptions. Others defied explanation. But here's the problem. The ocean sounds, the brine pools, and the giant creatures are symptoms of a deeper issue. The real question is not about any single phenomenon. The real question is whether our fundamental framework for understanding deep-sea biology is adequate, or whether it needs to be rebuilt from the foundations up. Consider the Yonaguni Monument. Located off the coast of Yonaguni Island, the westernmost island of Japan, this is a massive underwater rock formation discovered in 1986 by a local diver named Kihachiro Aratake. The structure consists of flat terraces, sharp edges, and what appear to be carved steps, columns, and channels, all submerged at a depth of approximately 5 to 40 meters. At first glance, it looks like the ruins of an ancient city. Marine geologist Masaki Kimura of the University of the Ryukyu studied the formation for years and concluded that it was a man-made structure, possibly a monument or ceremonial site constructed thousands of years ago when sea levels were lower and the formation was above water. Other geologists, including Robert Schoch of Boston University, argued that the formation was entirely natural, produced by the fracturing and erosion of the local sandstone along natural planes of weakness. The rock in the area is a fine-grained sandstone that naturally fractures in regular patterns, producing flat surfaces and sharp edges that can resemble human construction. The debate remains unresolved. The Yonaguni Monument sits at the intersection of geology, archaeology, and oceanography, and none of these disciplines can claim it definitively. but the case illustrates a broader truth about the ocean. Our ability to interpret what we see beneath the waves is constrained by our assumptions. We see patterns where we expect patterns. We find meaning where we expect meaning. And when the ocean shows us something that does not fit our expectations, our first instinct is to force it into a familiar framework rather than to question the framework itself. This brings us to the molecular biology of deep-sea survival, which represents perhaps the most profound challenge to our understanding of what is biologically possible, because the adaptations of deep-sea organisms extend far beyond anatomy, beyond the shape and size and color of their bodies. The adaptations reach down to the molecular level, to the very proteins and enzymes that make cellular life possible. At the pressures found in the Hadal zone, exceeding 1,000 atmospheres, the proteins that drive all biological processes would, in surface organisms, be crushed into non-functional shapes. The forces that maintain the three-dimensional structure of a protein, the hydrogen bonds and hydrophobic interactions that allow enzymes to catalyze reactions and membranes to form barriers, are disrupted by extreme pressure. This is not a subtle effect, it is devastating. A surface organism placed at Hadal depth would not just die from being crushed. Its cells would cease to function at the molecular level, its proteins unfolding, its membranes collapsing, its chemistry breaking down, before the structural failure of its body even became relevant. Deep-sea organisms have solved this problem through a class of molecules called piezolites. These are small organic compounds related to the osmolytes that other organisms use to cope with salt stress, that stabilize protein structure under extreme pressure. They work by altering the behavior of water molecules in the immediate vicinity of proteins, essentially changing the solvent environment, so that the protein remains folded and functional, despite the immense compressive force. Trimethylamine N-oxide, commonly abbreviated TMAO, is one of the best-studied piezolites. Its concentration in the tissues of deep-sea fish increases with depth, rising in a nearly linear relationship that tracks the increasing pressure. Fish from 5,000 meters have more TMAO than fish from 2,000 meters. Fish from 8,000 meters have to still more. This molecular adaptation imposes limits. At a certain depth, the concentration of TMAO required to stabilize proteins becomes so high that it interferes with other cellular processes. Scientists have calculated that this biochemical limit occurs at approximately 8,200 meters, which happens to correspond closely with the maximum depth at which fish have been observed. Below that depth, fish are absent. The deepest living fish ever recorded, a snailfish of the genus Pseudolaparis, was filmed at approximately 8,336 meters in the Izu-Ogasawara Trench. No fish has ever been confirmed deeper. The TMAO limit may be the reason. This molecular adaptation represents a complete re-engineering of cellular chemistry. It is as if the cells themselves have been rebuilt from the molecular level up, redesigned to function in an environment that is fundamentally incompatible with the biochemistry of surface life. The organisms of the deep ocean are not just surface organisms that have moved to greater depth. They are different machines, running the same general chemistry, yes, but with critical modifications that allow them to operate in conditions that would destroy their surface counterparts in seconds. The molecular divide between surface life and deep life is one of the most underappreciated findings in biology. We tend to think of life as a single phenomenon, governed by a single set of rules. The discovery of piezolites and the depth-dependent adaptation of deep-sea proteins tells a different story. It tells us that life is modular, that it can be fundamentally reconfigured at the molecular level to operate in radically different physical environments, and that the version of biochemistry that we study on the surface, the version taught in textbooks and researched in laboratories, is only one configuration among many. There is another phenomenon in the deep ocean that connects the surface world and the abyss in unexpected ways. Whale falls. When a large whale dies and its body sinks to the ocean floor, it creates a temporary but extraordinarily rich habitat that can sustain a specialized community of organisms for decades. A single whale carcass can weigh 40 to 80 tons, representing an enormous pulse of organic nutrients, arriving in an environment where food is otherwise desperately scarce. The progression of a whale fall community follows a predictable pattern. First, mobile scavengers, hagfish, sleeper sharks, and crabs arrive, stripping the soft tissue from the skeleton over a period of months to years. Then, a second phase begins, in which smaller organisms colonize the bones and surrounding sediment, feeding on the oils and fats that permeate the whale's skeleton. Finally, in the third and most remarkable phase, chemosynthetic bacteria colonize the bones, breaking down the lipids within the bone matrix and producing hydrogen sulfide as a byproduct. This hydrogen sulfide then supports a community of organisms that is strikingly similar to those found at hydrothermal vents, including specialized mussels, clams, and tube worms. The whale fall becomes, in effect, a temporary hydrothermal vent, a chemosynthetic island in the desert of the abyssal plain. Some researchers have proposed that whale falls may serve as stepping stones for vent organisms, providing temporary habitats along the dispersal corridors between distant vent sites. A lava drifting in the deep ocean currents might encounter a whale fall before reaching a new vent, settling there and surviving on the chemosynthetic resources of the decaying carcass until it can reproduce and send its own larvae onward. The distances between whale falls are shorter than the distances between vent sites, and whale falls may therefore function as biological bridges, connecting otherwise isolated chemosynthetic ecosystems. And then there is the question that haunts all of deep-sea biology, the question of how vent organisms colonize new vents. Hydrothermal vents are not permanent features. They are transient, lasting anywhere from a few decades to a few thousand years before the geological forces that created them shift. The flow of hot fluid ceases, and the vent dies. When a vent dies, the organisms that depend on it face a stark choice: find a new vent or perish. But vent sites are separated from each other by hundreds or thousands of kilometers of barren, lifeless seafloor. How do organisms that are utterly dependent on the specific chemistry of a hydrothermal vent manage to cross vast distances of hostile ocean to colonize sites they have never detected? The answer, as far as we understand it, involves the larval stage. Most vent organisms produce free-swimming larvae that are released into the water column and carried by deep ocean currents. These larvae are tiny, often less than a millimeter in length, and they do not feed during their dispersal phase. They survive on internal energy reserves, drifting with the currents for weeks or months, essentially gambling that the currents will carry them to a new vent before their energy is exhausted. The odds appear to be overwhelmingly against them. The ocean is immense. Active vents are tiny mole-scattered points separated by enormous distances. The chances of a single larva finding a suitable vent site should be vanishingly small. And yet, when new vents open, they are colonized rapidly, sometimes within months or even weeks. Organisms appear as though from nowhere, establishing populations with a speed that seems to violate the mathematics of random dispersal. Several explanations have been proposed. Some researchers believe that deep ocean currents create preferential transport corridors along the mid-ocean ridge, channeling larvae toward other vent sites rather than dispersing them randomly across the ocean floor. Others suggest that certain geological features, such as seamounts or fracture zones, act as stepping stones, providing temporary habitats where larvae can pause and refuel. Still others point to the possibility that some vent organisms can enter a state of metabolic dormancy, surviving in suspended animation for extended periods until they encounter favorable conditions. None of these explanations is fully satisfying. The dispersal problem remains one of the deepest unsolved puzzles in deep-sea biology. Something is wrong with our assumptions about how these organisms move through the deep ocean. Something about the mechanism of colonization does not match our models, and until we understand what that something is, we cannot claim to understand how vent ecosystems persist over time. The question of deep-sea mining makes this ignorance urgent. The International Seabed Authority has granted exploration contracts covering vast areas of the Pacific, Atlantic, and Indian Ocean floors. The Clarion-Clipperton Zone in the Central Pacific, a region roughly the size of the continental United States, is particularly targeted. This area is rich in polymetallic nodules, potato-sized lumps of manganese, nickel, cobalt, and copper that sit on the abyssal seafloor. These nodules formed over millions of years through the slow accumulation of dissolved metals from the water column. They provide hard substrate for organisms that cling to their surfaces in an otherwise featureless sediment plain. Mining these nodules would involve industrial-scale dredging of the seafloor, vacuuming up the nodules and the top layer of sediment, destroying the habitat and creating vast plumes of suspended sediment that could smother organisms over areas of hundreds of square kilometers. The sediment plumes would be carried by deep ocean currents, spreading the impact far beyond the immediate mining site. The organisms in the Clarion-Clipperton zone are not well known. Recent surveys have found that a large proportion of the species collected are new to science, found nowhere else. Destroying their habitat before they have been studied would be erasing pages from a book we have not yet read. The polymetallic nodules themselves are remarkable objects. They form through a process called hydrogenous precipitation, in which dissolved metals in the seawater slowly accumulate around a nucleus, often a shark tooth or a fragment of bone, growing at rates of only a few millimeters per million years. A single nodule the size of a potato may be 10 to 15 million years old. These are among the slowest forming structures in the natural world, slower than stalagmites, slower than coral reefs, slower than almost any other geological process that produces a discrete physical object. Mining them removes structures that took longer to form than the entire evolutionary history of the human species. The ecological impact would extend beyond the immediate destruction of the seafloor. The organisms that live on and around polymetallic nodules are specialists, adapted to the specific chemistry and texture of the nodule surface. Many of them are filter feeders, suspension feeders, and deposit feeders that rely on the hard substrate of the nodules for attachment in an otherwise soft, featureless plane of sediment. Remove the nodules, and you remove the only hard surface available for colonization over areas of thousands of square kilometers. The organisms that depend on those surfaces would have nowhere to go and nothing to attach to. Some estimates suggest that recovery of the seafloor ecosystem after nodule mining would take millions of years if it occurred at all. The nodules would not regrow on any human timescale. The sediment plumes would suffocate organisms across vast areas, and the species lost, many of them unknown to science, would be lost permanently. Their genetic information, their molecular adaptations, and their evolutionary history erased without record. There is also the problem of observation itself. When a submersible descends to a vent site, it brings with it light, noise, heat, and chemical emissions that are entirely foreign to the environment. Its mechanical arms can crush organisms, its thrusters can disturb sediment. The bright lights that illuminate the scene for cameras are, for organisms adapted to absolute darkness, the equivalent of a nuclear flash. The very act of looking changes what is being seen. Some researchers have begun developing less intrusive methods. Long-term cameras left at vent sites for months can record behavior in the absence of a submersible. Chemical sensors mounted on drifting platforms can sample the water without disturbing the seafloor. Acoustic instruments can map chimney structures from a distance. But these techniques are still in their early stages, and they provide only fragments of a picture that remains, in its entirety, beyond our current ability to capture. And there is one more angle that demands attention: the relationship between hydrothermal vents and the broader chemistry of the ocean. Vents do not just support local ecosystems, they influence the global ocean in ways that are only beginning to be measured. Hydrothermal vents inject massive quantities of dissolved chemicals into the deep ocean. Iron, manganese, helium, hydrogen sulfide, methane, and dozens of other compounds are released continuously by vent activity along the mid-ocean ridge. Some of these chemicals play critical roles far from their source. Iron, in particular, is a limiting nutrient for phytoplankton, the microscopic photosynthetic organisms that form the base of the surface food web and produce a significant fraction of the oxygen in the atmosphere. Studies have shown that iron from hydrothermal vents can be transported thousands of kilometers by deep ocean currents, eventually upwelling to the surface where it fertilizes phytoplankton growth. This connection is important because it means that the deep-sea volcanic systems are not isolated from the surface world. They are linked to it through the slow, vast circulation of the global ocean. The health of the surface, the productivity of the fisheries, the composition of the atmosphere itself may depend in ways we do not yet understand on the continuous chemical output of vents thousands of meters below. To disturb those systems without understanding their connections is to pull threads from a web whose structure we have not yet mapped. The connections extend further still. The water that circulates through hydrothermal vent systems undergoes chemical transformations that alter the composition of seawater itself. These transformations affect the pH of the ocean, the concentration of dissolved gases, and the availability of nutrients at all depths. The global ocean is a single interconnected chemical system. The processes occurring at hydrothermal vents are part of its fundamental chemistry, not a sidebar, not a local curiosity, but a global process with global consequences. We have now examined 5 different dimensions of the deep sea mystery. Brine pools, where life persists in conditions of extreme toxicity and salinity. Deep sea gigantism, where organisms grow to sizes that challenge our understanding of metabolic limits. Unexplained sounds, where the ocean produces signals we cannot conclusively identify. The Yonaguni Monument, where the boundary between natural process and human construction is blurred. And the molecular adaptations of deep sea life, where the fundamental machinery of biology has been re-engineered to function in an environment that should be lethal. Each of these mysteries has been investigated. Each has produced partial answers, and each, in the end, has revealed the same underlying truth. The deep ocean is far more complex, far more active, and far more alive than we ever imagined. And our understanding of it is not just incomplete, it is barely begun. There is a fact about our planet that should unsettle anyone who takes it seriously. We have explored more of the surface of the moon than we have explored of the floor of our own ocean. We have mapped more of the surface of Mars, using orbiting satellites and roving robots, than we have mapped of the terrain beneath our own waves. The deep ocean, which covers more than 60% of the Earth's surface and contains more than 97% of the planet's habitable volume, remains overwhelmingly unknown. Let that sink in. Current estimates, compiled from decades of bathymetric surveys, satellite altimetry, and ship-based sonar data, suggest that approximately 80% of the global ocean floor has never been mapped at a resolution sufficient to reveal features like hydrothermal vents, seamounts, or even moderately sized geological formations. 80%. 4/5 of the largest feature on our planet is essentially blank on our maps. We can point a telescope at a galaxy billions of light years away and determine its chemical composition, but we cannot tell you what the seafloor looks like 5 kilometers beneath a ship floating on the Pacific. This is not a failure of ambition. It is a failure of physics. In space, the primary challenge is propulsion, getting enough energy to escape the Earth's gravity and reach a destination. But once in space, the environment, while hostile, is transparent. Light travels unimpeded. Radio waves carry information at 300,000 kilometers per second. Cameras can photograph surfaces from orbit, mapping entire worlds in a single pass. The deep ocean offers none of these advantages. It is opaque, it absorbs light, it blocks radio waves, it resists radar. Every method of remote observation that works perfectly in space fails completely in water. Sound is the only form of energy that travels efficiently through the ocean. This is why deep-sea exploration relies so heavily on sonar, acoustic communication, on the interpretation of sound waves reflected from the seafloor and scattered by organisms in the water column. But acoustic methods are slow compared to electromagnetic ones. They are limited in resolution. They are distorted by variations in water temperature and salinity, which bend sound rays in unpredictable ways. Mapping the ocean floor with sonar is like trying to photograph a city by bouncing sound waves off its buildings from a mile away. You can determine the general shape, the rough layout, but the details, the textures, the inhabitants remain invisible. The technology gap is closing, but slowly. Autonomous underwater vehicles, known as AUVs, represent one of the most promising advances. These unmanned platforms can be programmed to follow predetermined paths across the ocean floor, collecting data on temperature, chemistry, and topography as they go. Some AUVs are equipped with side-scan sonar systems that can map the seafloor at resolutions of a few meters. Others carry chemical sensors capable of detecting the plume signatures of hydrothermal vents from kilometers away, following the dissolved chemical trail to its source, like a bloodhound tracking a scent. Still others carry high-definition cameras that can photograph the seafloor in detail, revealing organisms and features that sonar alone would miss. But AUVs are constrained by their battery life, their data storage, and the vast scale of the task. A typical AUV survey mission might cover a few hundred square kilometers over the course of a week. The ocean floor encompasses 361 million square kilometers. At current survey rates, a comprehensive high-resolution map of the entire ocean floor would require not decades but centuries, perhaps millennia. Remotely operated vehicles, or ROVs, provide a different kind of capability. These tethered robots, connected to a surface ship by a long umbilical cable of fiber optic strands and power conductors, can transmit high-definition video in real time and can be controlled by a human operator sitting in a climate-controlled room aboard the ship. The most advanced ROVs can operate at full ocean depth, more than 10,000 meters, and are equipped with robotic arms, sampling tools, cutting devices, and instrument packages that allow scientists to interact with the seafloor environment in ways that were impossible a generation ago. The development of these vehicles has been one of the great engineering achievements of the past half-century. Early ROVs were crude, limited in depth capability, and unreliable. Modern systems like JASON, operated by the Woods Hole Oceanographic Institution, or ROV Sebastian, operated by the Schmidt Ocean Institute, are precision instruments capable of delicate operations at full ocean depth. They can pick up individual organisms without damaging them. They can insert temperature probes into the throats of active vent chimneys. They can deploy and recover instruments that have been collecting data on the seafloor for months or years. And they can do all of this while transmitting live video to scientists on the surface and, increasingly, to audiences watching online in real time. Some of the most dramatic footage of deep-sea life in recent years has come from ROV dives that were live-streamed to millions of viewers, bringing the deep ocean into living rooms and classrooms for the first time in history. But ROV operations are expensive, requiring a large research vessel, a specialized crew, and millions of dollars in operating costs per expedition. Each dive covers only a small area of seafloor, perhaps a few hectares. The world's fleet of deep-capable ROVs numbers in the dozens. The number of active vent sites on the mid-ocean ridge alone may be in the thousands or tens of thousands. The gap between our capacity for observation and the scale of what needs to be observed is not closing. It may be widening, as new discoveries reveal the extent of what remains unknown. The result is that our picture of the deep ocean is built from an absurdly small number of data points. We have taken a few thousand sediment cores from a sea floor that spans hundreds of millions of square kilometers. We have conducted a few hundred submersible dives to hydrothermal vent sites along a ridge system that wraps around the entire planet. We have placed a handful of long-term monitoring stations at a small number of carefully selected locations. Our understanding of the deep ocean is assembled from these scattered observations, like trying to reconstruct a jigsaw puzzle of 1,000,000 pieces using only 100. What we have found, even with these limited observations, has been extraordinary. But what remains hidden may be far more significant. And the discovery that best illustrates this possibility is the deep subsurface biosphere. In the 1990s, drilling projects conducted by the Ocean Drilling Program and its successor, the Integrated Ocean Drilling Program, began recovering rock and sediment samples from deep beneath the ocean floor. The original goal was geological, to study the structure and composition of the oceanic crust. But the samples contained something that no one had expected: living microbial cells, buried in rock and sediment more than 2.5 kilometers below the seafloor. These organisms exist in conditions that push the definition of life to its absolute boundary. They live in total darkness, under immense pressure, in pore spaces within solid rock so small that they can barely be seen with a microscope. They have no access to sunlight, no connection to the open ocean, and no obvious energy source. Their metabolisms operate at speeds so slow that they are nearly undetectable with standard laboratory techniques. Where a surface bacterium divides every 20 minutes, producing a new generation in the time it takes to eat lunch, a deep subsurface bacterium may divide once every 100 years, or once every 1,000 years. Their timescale is not biological in any way we normally understand the word. It is geological. The energy sources available to these organisms are meager beyond ordinary comprehension. Some appear to derive energy from the radiolysis of water, a process in which the natural radioactive decay of elements like uranium, thorium, and potassium in the surrounding rock splits water molecules, producing tiny amounts of hydrogen gas. The microbes oxidize this hydrogen, extracting a vanishingly small amount of energy from each reaction, enough to maintain their cellular machinery, enough to repair their DNA, enough to survive, but barely more. Others may be sustained by serpentinization reactions occurring deep within the crust, the same rock-water chemistry that powers the Lost City vent field, but taking place in tiny fractures and pore spaces far below the visible seafloor. The total biomass of the deep subsurface biosphere is staggering. Current estimates suggest that the mass of all microbial life living within the rock and sediment beneath the ocean floor may equal or exceed the mass of all life in the ocean above it. Billions of tons of living material, hidden in stone, invisible, silent, operating on timescales that dwarf human civilization. This is not a fringe community of desperate survivors clinging to existence at the edge of possibility. This is a massive planet-scale ecosystem that pervades the upper crust of the Earth, and we had no idea it existed until a few decades ago. Let that sink in. There may be as much life hidden in the rock beneath the seafloor as there is in the entire ocean water column above. An entire biosphere, invisible, unknown, operating in conditions so extreme that most biologists would have said they were incompatible with life of any kind. This is not science fiction. This is the current state of scientific understanding, published in peer-reviewed journals, based on samples recovered from drilling sites across the global ocean. The deep subsurface biosphere is real, it is enormous, and its discovery is one of the most profound biological findings of the past century, ranking alongside the discovery of vent ecosystems in its implications for how we understand life. The deep subsurface biosphere forces us to reconsider what we mean by the word alive. These organisms do not grow, reproduce, move, or respond to their environment in any time frame that a human could observe. If you watched one of these cells through a microscope for an entire human lifetime, you might not see it divide even once. Its metabolism is so slow that the chemical reactions sustaining it produce energy at rates barely distinguishable from the background noise of non-biological chemistry. And yet the cell maintains its integrity, repairs its DNA when it is damaged by radiation, and presumably, over centuries, produces a daughter cell that is a faithful copy of itself. This challenges one of the basic intuitions we have about life, the intuition that life is active, dynamic, and visibly different from non-life. In the deep subsurface, the line between living chemistry and non-living chemistry becomes blurred. The organisms exist in a state that is neither fully alive in the surface sense nor fully dead. They persist, they endure, they occupy a metabolic twilight zone where the distinction between biology and geology becomes uncertain. Some researchers have proposed that these organisms represent a form of life that is fundamentally different from anything we study on the surface, not different in its basic chemistry, which still involves DNA, proteins, and the familiar molecular machinery of all known life, but different in its relationship to time. Surface life lives fast and dies fast. Deep subsurface life lives slow and endures for ages. The two modes of existence represent opposite ends of a spectrum, and the deep end of that spectrum may be far more representative of life in the universe than the surface end. If most habitable environments in the universe are subsurface, hidden beneath ice or rock, cut off from starlight, powered by meager chemical reactions, then the dominant form of life in the cosmos may not be anything like the busy, fast-metabolizing, rapidly reproducing organisms of Earth's surface. It may be more like the deep subsurface microbes, slow, silent, ancient, and patient beyond human comprehension. What does this mean for the search for life beyond Earth? It means that the universe of potential habitats for life has expanded enormously. Every rocky body with liquid water in its interior becomes a candidate. Europa, the ice-covered moon of Jupiter, harbors a global ocean beneath its frozen surface. Current estimates suggest that this ocean may contain twice as much liquid water as all of Earth's oceans combined. The ocean is kept liquid by tidal heating, the flexing of Europa's interior caused by Jupiter's immense gravity, which generates enough heat to maintain liquid water, despite the moon's distance from the sun. If hydrothermal activity or serpentinization is occurring at Europa's rocky seafloor, then the chemical conditions for chemosynthetic life may already exist there. Not in theory, in practice. Enceladus, a small moon of Saturn barely 500 kilometers in diameter, provides even more direct evidence. In 2005, the Cassini spacecraft observed plumes of water vapor and ice particles erupting from fractures near the south pole of Enceladus. These plumes were jetting material from the moon's subsurface ocean directly into space, where it could be sampled by the spacecraft's instruments. Analysis of the plume material revealed the presence of molecular hydrogen, silica nanoparticles, and simple organic molecules. The hydrogen is significant because it is a chemical signature of hydrothermal reactions, specifically serpentinization, the same process that powers the lost city vents on Earth. The silica nanoparticles suggest high-temperature water rock interactions consistent with hydrothermal venting at the moon's ocean floor. Enceladus is venting the chemical products of hydrothermal activity into space. The ingredients for chemosynthetic life are present. The energy source is there. The liquid water is there. The organic chemistry is there. Whether life itself is there remains unknown. But the conditions necessary for it, based on everything we have learned from Earth's deep ocean, appear to be met. The significance of this cannot be understated. For the first time in the history of science, we have identified a world other than Earth, where the specific conditions known to support life on our own planet appear to exist. Not vaguely analogous conditions, specific conditions, hydrothermal chemistry, liquid water, organic molecules, hydrogen gas. The same chemical ingredients that power the vent ecosystems we have spent 5 decades studying on Earth are present on a moon of Saturn. The connection between the deep ocean and the search for extraterrestrial life is not metaphorical. It is direct and concrete. Future missions to Europa and Enceladus will be designed, in large part, based on what we have learned from studying hydrothermal vents on Earth. The instruments that will search for signs of life in Europa's ocean or in the plume material of Enceladus will be calibrated to detect the chemical signatures of chemosynthesis, the same signatures that scientists first measured at the Galapagos Rift in 1977. The deep ocean is not just informing the search for extraterrestrial life, it is defining it. The questions we ask, the instruments we build, the biosignatures we look for, all of them are shaped by what the deep ocean has taught us about the minimum requirements for life. The concept of the habitable zone illustrates how dramatically the deep ocean has reshaped our thinking. Traditionally, the habitable zone of a star was defined as the narrow band of distances at which a planet could have liquid water on its surface. Too close to the star, and the water boils away. Too far, and it freezes solid. Earth sits comfortably within the habitable zone of our Sun, and for decades, that was considered one of the principal reasons our planet supports life. But the discovery of subsurface oceans on icy moons has shattered this tidy concept. Europa and Enceladus are far outside the traditional habitable zone. Their surfaces are frozen solid, scoured by radiation, with temperatures hundreds of degrees below zero. No surface life could survive there for an instant. And yet, beneath their ice, there are oceans of liquid water, maintained not by sunlight but by internal heat sources, tidal flexing, radioactive decay, and the heat generated by serpentinization reactions. The habitable zone, it turns out, is not a narrow ring around a star. It is any location in the universe where liquid water coexists with a source of chemical energy and the raw materials for organic chemistry, and hydrothermal vents, powered by the internal processes of a world, rather than by the light of a distant star, prove that such locations can exist essentially anywhere. This realization transforms the mathematics of life in the universe. Under the old definition of the habitable zone, The number of potentially life-bearing worlds was limited to rocky planets orbiting at just the right distance from their hosted stars. Under the new definition, which the deep ocean demands, the number expands by orders of magnitude because it includes every icy moon, every rocky body, every world with a subsurface ocean and geological activity, regardless of its distance from a star. The implications ripple outward to cosmic scales. If every rocky moon with a subsurface ocean and geological activity is a potential habitat for life, then the number of habitable worlds in our galaxy is not in the dozens or hundreds. It is in the billions. Jupiter has 4 large moons, and at least 2 of them, Europa and Ganymede, are believed to have subsurface oceans. Saturn has Enceladus, which is actively venting ocean material into space. Neptune's moon Triton shows signs of geological activity. If similar systems exist around other stars, and there is no physical reason to believe they would not, then the ocean is not a rare feature in the universe. It is common, and hydrothermal systems, or their chemical equivalents, may be equally common. Current estimates suggest that there are between 100 billion and 400 billion stars in the Milky Way galaxy alone. Many of these stars have planetary systems. Many of those systems include gas giant planets with moons. Based on what we have observed in our own solar system, a substantial fraction of those moons may harbour subsurface oceans. The European Space Agency has estimated that ocean worlds, bodies with significant volumes of liquid water either on the surface or beneath ice, may outnumber dry, rocky worlds by a factor of 10 or more. If that estimate is even approximately correct, then the total number of ocean worlds in our galaxy alone could be in the tens of billions, each one a potential habitat for chemosynthetic life. Not everyone will have the right chemistry. Not everyone will have the energy sources needed. Not everyone will support the molecular complexity necessary for living systems to emerge. But even if a vanishingly small fraction of them, 1% or 1/10 of 1%, harbours conditions suitable for life, the numbers are still enormous. Tens of millions of potentially living worlds in a single galaxy. There is a concept in biology called convergent evolution, the observed tendency of unrelated organisms to develop similar solutions to similar problems. Wings evolved independently in birds, bats, insects, and pterosaurs. Eyes evolved independently in vertebrates, mollusks, and arthropods. Streamlined body shapes evolved independently in dolphins, sharks, ichthyosaurs, and tuna. When the physical or chemical problem is the same, the biological solution is often the same, even when the organisms involved share no recent common ancestry. If convergent evolution operates beyond Earth, then the biological solutions found by deep-sea organisms on our planet may be universal. Chemosynthetic metabolism, symbiotic partnerships between microbes and multicellular hosts, piezolyte-mediated pressure tolerance, heat shock protein protection at extreme temperatures, these may not be Earth-specific innovations. They may be general solutions that life converges on wherever it faces the same physical and chemical challenges. The logic is compelling. The laws of physics and chemistry are the same everywhere in the universe. Hydrogen sulfide is toxic in the same way on Europa as it is on Earth. Pressure compresses proteins in the same way on Enceladus as it does in the Mariana Trench. If life exists in these environments, it faces the same problems, and convergent evolution predicts that it will find the same solutions. The tube worm's trophosome, the partnership between a multicellular host and chemosynthetic bacteria, may be reinvented independently on any world where similar conditions prevail. The concept is not that extraterrestrial life will look like Earth life in its surface details. It is that the deep architecture, the metabolic strategies, the molecular adaptations, the fundamental solutions to the problem of surviving in a dark, pressurized, chemically active environment may be convergent across the cosmos. This is a profoundly different vision of life in the universe from the one that dominated science fiction and popular imagination for most of the 20th century. The popular image of extraterrestrial life was shaped by the assumption that life requires conditions similar to the Earth's surface: warmth, light, oxygen, moderate pressure. The aliens of science fiction lived on the surfaces of their worlds, under open skies, breathing atmospheres. The deep ocean has replaced that vision with something far stranger, and in many ways, far more likely. Life in the universe may be predominantly dark, hidden, pressurized, and chemical. It may exist not on the surfaces of worlds but inside them, beneath ice or rock, in oceans that never see a star. We may already know, in broad outline, what life looks like on Europa or Enceladus, not because we have visited those worlds, but because we have visited the deep ocean. The hydrothermal vent is a rehearsal. The creatures that live there are previews of a biological reality that may extend across the cosmos. The deep ocean is not a frontier to be conquered. It is a teacher. It has been running experiments in extreme biology for longer than we can measure, testing the boundaries of what life can tolerate, what life can exploit, and what life can become under conditions that we are only now beginning to explore. Every vent field we discover, every new organism we describe, every metabolic pathway we map is a lesson, and the most important lesson of all may be the simplest one. Life does not need what we assumed it needed. It needs less, it tolerates more, and it exists in places we never thought to look. What does it mean for humanity when the most alien life on our planet lives right beneath us? This is not a rhetorical question. It carries weight. It carries urgency, because the discoveries of the past 5 decades, from the Galapagos Rift to the Lost City, from the brine pools of the Red Sea to the deep subsurface biosphere, have not merely expanded our catalogue of known species. They have challenged the foundational framework of biology itself. For most of human history, life was understood through the lens of the surface. Life needed sunlight. Life needed oxygen. Life needed moderate temperatures and liquid water at the surface. These were not considered hypotheses. They were treated as axioms. Every ecosystem that humans had ever studied seemed to confirm them. Forests, grasslands, coral reefs, lakes, deserts, tundra, all powered, directly or indirectly, by the energy of the sun. That framework is broken. Chemosynthetic ecosystems at hydrothermal vents proved, without ambiguity, that life can operate in total independence from solar energy. Organisms thriving at temperatures exceeding 100 degrees Celsius, at pressures greater than 1,000 atmospheres, in water saturated with hydrogen sulfide and dissolved metals, demonstrated that the boundaries of biological tolerance are far wider than anyone had imagined. And the deep subsurface biosphere, living within the rock of the ocean crust itself, demonstrated that life does not even require an open environment. It can persist in the pore spaces of solid stone, sustained by chemical reactions so slow that a single cell division takes a century. The philosophical weight of this realization is substantial. If life is this adaptable, this resilient, this willing to exploit any available energy source in any available environment, then the universe is a profoundly different place than the one imagined by scientists a century ago. A century ago, life was understood to be fragile, rare, and special. It required conditions so precise and narrow that Earth might have been the only place in the universe where they existed. That understanding has been demolished by what we have found in the deep ocean. Life, as we now understand it, is not fragile. It is robust. It is not rare. It is probably common. And it does not require the precise narrow conditions of the surface. It requires only 2 things: a source of chemical energy and a medium in which chemical reactions can occur. There is a philosophical pause worth taking here. We spend enormous resources searching for life on other worlds. We point radio telescopes at distant stars. We send rovers to Mars. We plan missions to Europa and Enceladus. We design instruments that could detect biosignatures in the atmospheres of exoplanets orbiting stars dozens of light years away. All of this work is valuable. All of it is driven by one of the deepest human desires, the desire to know whether we are alone. But while we look outward with such intensity, there is a world directly beneath us, beneath our oceans, beneath the thin skin of rock and water that separates the surface from the interior of our own planet, that we have barely begun to explore. The deep ocean is not a distraction from the search for extraterrestrial life. It is the search for extraterrestrial life conducted on the only world where we can currently study it directly and conclusively. Every hydrothermal vent we characterize, every chemosynthetic organism we describe, every extreme environment we map, brings us closer to understanding what life might look like on another world. And the answer, increasingly, is it might look remarkably like what we have already found. dark, pressurized, and chemical, hidden beneath ice or rock or kilometers of cold water. There is something deeply humbling about this realization. For centuries, we built our picture of life around what we could see. We studied the organisms of our own environment, the plants and animals and fungi and bacteria of the sunlit, oxygenated, moderate temperature surface. We constructed our entire biological framework around their needs, their chemistry, their limitations. And then we descended into the darkness and discovered that the surface rules do not apply. The creatures we found there did not need our sunlight. They did not need our oxygen. They did not need our temperatures or our pressures or our food chains. They had built their own world, powered by their own energy, governed by their own rules. And they had done this in a place that every surface-dwelling biologist had dismissed as lifeless. That dismissal was not a failure of data. It was a failure of imagination. We could not conceive of life without the sun because we had never seen it in the dark. We could not imagine biology without photosynthesis, because photosynthesis was all we knew. And so we drew the boundaries of the living world around our own experience, and excluded the vast majority of the planet from consideration. The deep ocean, the single largest habitat on Earth, was written off as a biological wasteland for centuries, simply because no one had looked carefully enough to see what was actually there. This is a pattern that appears throughout the history of inquiry. We define the possible in terms of the familiar, and then we are startled when nature proves more inventive than our definitions allow. We assume the Earth was the center of everything because that was where we stood. We assumed the continents were fixed because we could not feel them move. We assumed the atom was indivisible because we could not see inside it. And we assumed the deep ocean was lifeless because we had not descended into it. Each assumption was shattered by observation, by the simple act of looking at the world with better instruments and fewer preconceptions. The moral implications are inescapable. If the deep ocean harbors ecosystems that are scientifically irreplaceable, ecologically unique, and potentially analogous to life on other worlds, then we have a responsibility to protect it. Deep-sea mining, bottom trawling, pollution, ocean warming, and acidification all threaten the deep ocean in ways that may be irreversible. The organisms at hydrothermal vents cannot migrate. They depend on specific chemical conditions at specific geological locations. If those locations are mined, drilled, or otherwise destroyed, the organisms are gone, not displaced, not relocated, extinct. And extinction in the deep ocean carries a particular weight, because the organisms being lost may be irreplaceable in a way that surface extinctions are not. When a rainforest species goes extinct, its ecological role may eventually be filled by another species through the process of adaptive radiation. The niche remains, and over evolutionary time, something will fill it. But the organisms at hydrothermal vents occupy niches that are defined not just by ecology but by chemistry and geology. They depend on specific mineral compositions, specific temperatures, specific flow rates of specific chemicals from specific geological formations. If a vent field is destroyed by mining, the geological conditions that created it may not be replicated anywhere else on Earth. The organisms that depended on those conditions, organisms with unique enzymes, unique metabolic pathways, and unique molecular adaptations are gone forever. And with them go potential insights into the chemistry of life, the limits of biological tolerance, and the conditions that might support life on other worlds. There is a bitter irony here. The minerals that the mining industry seeks from the deep sea, cobalt, nickel, manganese, and rare earth elements, are needed in large part for the production of batteries and electronics, technologies that are essential for the transition away from fossil fuels. The clean energy economy requires materials that are currently most abundant in the deep ocean. Protecting the deep ocean from mining may complicate the effort to address climate change, but destroying the deep ocean to save the surface climate would be a Pyrrhic victory, solving one environmental crisis by creating another that may be even more permanent. The oceans are warming. The deep ocean absorbs a significant portion of the excess heat generated by greenhouse gas emissions. More than 90% of the additional thermal energy trapped by greenhouse gases since the Industrial Revolution has been absorbed by the ocean. This heat penetrates slowly, carried downward by the global thermohaline circulation. the great conveyor belt of ocean currents, driven by differences in water temperature and salinity. It takes decades or centuries for surface warming to reach the deepest layers, but it is reaching them. Current measurements from deep ocean temperature sensors indicate that even the abyssal waters, at depths of 4,000 to 6,000 meters, are gradually warming. The rate of deep ocean warming is slow by human standards, fractions of a degree per decade, but it is occurring against a backdrop of extraordinary thermal stability. The organisms of the deep ocean have adapted to temperatures that have been essentially constant for thousands of years. A change of even half a degree may represent the largest thermal perturbation these organisms have experienced in their evolutionary history. Some species may be able to adapt. Many, particularly those with narrow thermal tolerances, may not. And because deep-sea organisms generally have slow metabolic rates, long generation times, and limited genetic diversity, their capacity for rapid evolutionary adaptation is likely far lower than that of surface species. The consequences for deep-sea organisms, many of which have adapted to temperatures that have been stable for millennia, are unknown. We cannot predict which species will survive and which will not, because we have not studied the vast majority of them well enough to understand their thermal tolerances. We are, in effect, changing the rules of an environment that we have barely begun to explore. Ocean acidification adds another dimension of risk. As atmospheric carbon dioxide increases, a fraction is absorbed by the ocean, where it reacts with seawater to form carbonic acid, gradually lowering the pH. The surface ocean has already become approximately 30% more acidic since the beginning of the industrial era. The effects on surface organisms, particularly corals, mollusks, and other calcifying organisms, are already being documented with increasing alarm. The effects on deep-sea organisms are far less understood. Cold water corals, which form habitat for hundreds of other species on seamounts and along continental margins, build their skeletons from calcium carbonate. Foraminifera, tiny shell-building organisms found at all ocean depths, rely on the same chemistry. If the water becomes too acidic, these structures dissolve. The habitats they create collapse. The communities they support disappear. The interconnections between surface changes and deep-sea consequences are poorly understood, and this ignorance carries risk. The deep ocean is not a sealed vault, insulated from the surface by kilometers of water. It is connected to the surface through the global circulation of ocean currents, through the sinking of cold, dense water at the poles that eventually reaches the abyss, through the endless rain of marine snow that carries surface nutrients to the deep sea floor. Changes at the surface propagate downward, and changes in the deep propagate upward, through upwelling currents, through the cycling of carbon and nutrients, through the chemical processes that regulate the entire ocean system. The deep ocean also plays a critical and poorly appreciated role in regulating the global climate. The abyssal waters store vast quantities of dissolved carbon dioxide, keeping it out of the atmosphere. The slow circulation of the thermohaline conveyor, which moves cold, dense water from the poles through the deep ocean basins, and eventually brings it back to the surface, centuries later, acts as a planetary thermostat, buffering temperature changes and distributing heat across the globe. Any disruption of this deep circulation, whether caused by warming, freshwater input from melting ice sheets, or changes in ocean chemistry, could have cascading effects on the global climate system that would dwarf the changes we have experienced so far. The relationship between the deep ocean and the atmosphere is a two-way street. The atmosphere affects the deep ocean through the slow penetration of heat and dissolved gases. The deep ocean affects the atmosphere through the eventual upwelling of nutrient-rich, carbon-laden water that feeds surface productivity and releases stored carbon dioxide. We are altering one side of this relationship, the atmospheric side, at a rate that is unprecedented in the geological record. What happens to the other side, the deep ocean side, is a question that we cannot yet answer with confidence. We are, in the most literal sense, the first generation that understands what the deep ocean contains. Before 1977, no one knew that chemosynthetic ecosystems existed. Before 1960, no one had reached the deepest point in the ocean. Before the development of remotely operated vehicles and autonomous underwater platforms, no one could explore the deep with any consistency. We are the first humans in history to have seen these things. And that makes us the first humans in history who can make informed decisions about their fate. The choices made in the coming decades will determine whether the deep ocean remains a living archive of Earth's biological potential or becomes a depleted resource, stripped of its mineral wealth and diminished in its biological diversity. The exploration licenses have already been issued. The mining technology is being tested at prototype scale. The economic incentives are enormous. The only counterbalance is knowledge, awareness, and the moral conviction that some things are worth more than their mineral content. And what we know at the most fundamental level is this. The deep ocean is not a wasteland. It is not empty. It is not a dark, lifeless void waiting to be filled with human industry. It is alive. It is ancient. It is complex beyond our current ability to measure. And it may hold the key to understanding the most important question in all of science. Not just whether other worlds have life, but what life truly is. The ocean does not care whether we understand it. It was here before us. It will be here after us. Its hydrothermal vents were pouring chemical energy into the darkness long before the first human eye opened, and they will continue long after the last one closes. The tube worms do not wait for our permission to grow. The chemosynthetic bacteria do not require our validation to metabolize. The deep subsurface microbes, dividing once per century in their silent stone chambers, are not aware of our existence and would not be altered by it. This is the central truth of the deep ocean. It operates independently of us. It obeys its own rules. It sustains its own life. It runs its own experiments in biochemistry and adaptation and survival. And it does all of this in a darkness so complete that our most powerful lights illuminate only a tiny sphere around the vehicle we have sent to observe it, a sphere that vanishes into the black the moment we leave. We are visitors in the deep ocean, brief, clumsy, disruptive visitors. We bring light where there has never been light. We bring noise where there has been only silence. We bring instruments and sampling devices and cameras and mechanical arms. And we reach into a world that has been functioning without us for eons. And we try to understand it in the few hours before our batteries die, and our oxygen runs low, and the surface calls us back. And yet, those visits have changed us. They have changed what we know about life. They have changed what we consider possible. They have changed how we define the word habitable. They have changed how we think about our place on this planet, and our prospects for finding kindred biology on other worlds. A few hundred dives, a few thousand hours of observation have overturned assumptions that stood for centuries. Roll footage, a research vessel at anchor in open ocean at twilight, scientists on deck looking out at the darkening water in quiet contemplation, the glow of instrument screens illuminating faces in a dimly lit control room, a submersible being winched back aboard after a dive, water streaming from its hull. The discovery of hydrothermal vent ecosystems is, by any measure, one of the most important scientific findings in living memory. It belongs alongside the discovery of the structure of DNA, the confirmation of plate tectonics, and the detection of the cosmic microwave background as a moment that fundamentally altered the human understanding of how the world works. And unlike many of those discoveries, which built gradually from decades of theoretical groundwork, the vent discovery was a surprise. No one predicted it in its full biological dimensions. No one expected to find thriving ecosystems powered by volcanic chemistry in total darkness, populated by animals with no digestive systems and shrimp that see heat. It was an act of looking where no one had looked before, and finding something that rewrote the rules. That act of looking is not finished. It is barely begun. More than 95% of the ocean floor remains unseen by human eyes or instruments. The mid-ocean ridge system, the largest geological structure on Earth, has been surveyed at only a small fraction of its total length. Entire vent fields exist right now, at this moment, in the darkness beneath the waves, teeming with organisms that no scientist has ever described, running on chemistry that no laboratory has ever analyzed. Every future dive has the potential to reveal something that changes what we think we know. The history of deep-sea exploration is a history of humility forced upon the arrogant. Every time we have predicted what the deep ocean would contain, we have been wrong. Scientists predicted the ocean floor would be lifeless. It was teeming. Scientists predicted that the deepest trenches would be devoid of complex organisms. They found fish. Scientists predicted that life requires sunlight. They found ecosystems that run on volcanic chemistry. Scientists predicted that the rock beneath the ocean floor would be sterile. They found a biosphere that may rival the ocean itself in total biomass. At every turn, the deep ocean has exceeded our expectations and mocked our limitations. What will the next dive reveal? What organisms are waiting right now at the next vent field that no one has yet visited? What metabolic pathways are being run at this very moment by bacteria in the deep subsurface that no one has yet sampled? What fundamental processes, what basic principles of how life works, are still hidden in the darkness, waiting for a submersible, or an ROV, or an AUV, or some technology not yet invented, to descend and shine a light? We do not know. And that is the point. The deep ocean is a reminder that the world is larger than our knowledge of it, that life is more resourceful than our theories predict, that the most important discoveries are often made not by looking where we expect to find something, but by looking where we expect to find nothing. The tube worms of the Galapagos Rift did not care that biologists had declared their habitat uninhabitable. The bacteria of the lost city did not care that their energy source was supposed to be insufficient. The microbes of the deep subsurface did not care that their stone prisons were supposed to be sterile. Life did not consult our textbooks before deciding where to grow. It simply grew. Perhaps that is the most important lesson. Not what we found at hydrothermal vents, but what those findings reveal about the limits of our own understanding. We drew a circle around the conditions that we believed life required, and life stepped outside that circle. We defined the habitable zone, and life proved the definition wrong. We called the deep ocean barren, and it showed us ecosystems richer and stranger than anything in our experience. There is a kind of arrogance in assuming that we know where life can and cannot exist, an arrogance that is quietly but decisively being dismantled by the creatures of the deep. They do not argue with our theories. They simply exist in places where our theories say they should not, and by existing, they teach us that the boundaries of life are not what we thought, that the universe of the living is wider and darker and more chemically inventive than any surface-dwelling mind had conceived. The darkness at the bottom of the ocean is not empty. It never was. It is full of fire and chemistry and patience, full of organisms that have solved the problem of existence in ways that our surface-dwelling imaginations could not have invented, full of answers to questions we have not yet learned to ask, full of mysteries that will occupy scientists for centuries to come, if we have the wisdom to preserve the deep long enough to study it. Somewhere, right now, at the bottom of a trench we have never explored, along a ridge we have never mapped, in rock we have never drilled, there are living things, thriving things, things powered by the earth itself, by the slow heat of the interior, by the ancient and ceaseless chemistry of water and stone. They do not need sunlight. They do not need the surface. They do not need us. And they have been there all along, before we had a name for them, before we had instruments to detect them, before we understood that the rules we wrote for life on the surface were never the only rules. They were there, in the dark, running on fire, and they will be there long after we are gone.